Let's perform a few more exercises applying the equilibrium equations to 4 different examples. As a review, we have 2 equations or 2 conditions for equilibrium. The first condition is that the sum of all forces must be 0. To apply this, you need to do the following. First, you need to identify the forces acting on the body or on each of the bodies. And then you need to draw a free body diagram on each of the bodies. Next, you need a reference system. So you draw a reference frame. And the typical reference frame that we use is the Cartesian coordinate system. And then you apply Newton's second law of motion. Newton's second law of motion. By summing the forces along each axis and then equating them to 0. Finally, solve for the unknowns. The second condition for equilibrium is that the sum of all torques must be 0. To apply this, the following must be done. First, you need to identify the forces acting on the body. And then you identify the axis of rotation. Or the fulcrum. Then you identify the moment arm or the lever arm. Next, you draw as reference the positive direction of the torque. And then you apply Newton's second law of motion by summing all the torques and equating them to 0. Finally, you solve for the unknowns. Now let's solve our first problem. And our first problem involves calculating the mass m needed in order to suspend the leg as shown in the figure. Assume that the leg with cast has a mass of 15 kilograms and its center of gravity is 35 centimeters from the hip joint. The sling is 80.5 centimeters from the hip joint. So as we've discussed earlier, we first need to identify the forces. As we know, gravity is always present, and gravity acts on the center of gravity of the object. So this is where gravity should be found. The mass is 15 kilograms, and if you multiply that by 9.8 meters per second, that's the weight. The next force is the tension, which pulls the leg upward. The tension is applied here. So let's call that T. The next thing we need to do is to identify the axis of rotation. As we know, if this mass goes down, the whole leg goes up, and it goes up with having this as the axis of rotation, which means we identify the hip joint as the axis of rotation or the fulcrum. Next is we identify the moment arm or the lever arm. So for the center of gravity or for the gravitational force, the lever arm is 35 centimeters from the hip joint. So the distance is 35 centimeters, and the lever arm vector is from the hip joint to the center of gravity. As you can see, the lever arm and the gravitational force are perpendicular to each other. This angle is 90 degrees. The tension is located 80.5 centimeters from the hip joint. So that's 80.5 centimeters. We also see that the lever arm for the tension is perpendicular to the tension. That is, the angle between them is also 90 degrees. Next is we draw as reference the positive direction of the torque. We can draw a counterclockwise direction as the positive direction for the torque. We see that the gravitational force causes a clockwise rotation with respect to the hip joint, which means that this torque has a negative sign. On the other hand, the tension causes a counterclockwise direction with respect to the hip joint. This means that this torque produced by the tension has a positive direction. So if we sum all the torque about the axis where the hip joint is located, we get the following. 0.35 meters, that's 35 centimeters, or the distance of the center of gravity from the hip joint, multiplied by 15 kilograms times 9.8 meters per second squared, which is the weight of the whole leg. And we know that this torque is negative because, as we discussed, this causes a clockwise direction, which is a negative torque. The second torque is located 80.5 centimeters or 0.805 meters from the hip joint, and the force is due to the tension, and this causes a positive torque, and that should be equal to 0. Now we can easily solve for the tension as shown, but we don't really need to solve for the tension. What we need to do is to relate this tension to the mass m, because that's what's required in this problem. So how do we relate that tension T to the mass m? Let's first focus on the mass m. On the mass m, there are two forces acting on it. We have the tension due to the string, which we now call as T prime, and the weight of the mass, which we call as mg. There are no forces along the x-axis. If we sum the forces along the y-axis, we have T prime minus mg equals 0. If we choose this direction as the positive direction. So we have T prime equals mg. Now how is T prime related to T? T prime is the force exerted by the string on the block. According to Newton's third law of motion, there is also an equal and opposite force exerted on the string by the block, which is in this direction. In the same way, the string exerts a force of equal magnitude but opposite in direction to the sling. According to Newton's third law, the reaction force is also in this direction. And from here we see that these two forces are equal according to Newton's third law of motion. So we write, according to Newton's third law of motion, T prime is equal to T, which means that we can replace this T by mg. Now we can compute for the mass m using this equation. So m will be equal to negative 0.35 meters times 15 kilograms times 9.8 meters per second squared divided by 0.805 meters times 9.8 meters per second squared. This cancels, of course, and we solve for the mass to be equal to 6.5 kilograms. So in order for the hip joint to be hung or suspended as shown in the figure, the mass has to be equal to 6.5 kilograms. In this next problem, there's a 72 kilogram man who is suspended as shown using his two hands. His hands are separated 36 centimeters apart, and his center of gravity is located 75% of the distance from his right hand towards his left. So if this is his right hand, and this is his left hand, and this is the distance between the two hands, somewhere here is his center of gravity, which is 75% of 36 centimeters. So 75% of 36 centimeters is 27 centimeters. So this is 27 centimeters, and this is 9 centimeters. So this is also an equilibrium problem. The first thing that we need to do is to identify the forces acting on the man. So the forces acting on him are the force exerted by the floor on his right hand. So let's call that NR. The force exerted by the floor on his left hand, let's call that NL. And the force exerted by gravity on his center of gravity, and let's call that just simply mg. Okay, now we have two unknowns. The unknown quantities are nr and nl. How do we solve for these unknown quantities if we only have one quantity that is known? We also know, of course, the distances of the center of gravity with respect to the left hand and the right hand. So obviously this is a torque problem, or this is an equilibrium problem, where we use both sum of forces and sum of torques. If we sum the forces on this person's body, we notice that there's no force along the x-axis, so we sum only the forces along the y-axis. So summing the forces along the y-axis, choosing upward direction as the positive direction, we have nr plus nl minus mg equals 0. Now let's sum all the torques. We have already identified the three forces. Next thing we need to do is to identify the axis of rotation, or the fulcrum. As we discussed in the lecture, we can choose any point to be the axis of rotation. If we choose the weight, or the center of gravity, to be the axis of rotation, then we end up with two unknowns in our equation, nr and nl. If we choose nr as the axis of rotation, then we end up with an equation where nl is the only unknown. So let's do that. Let's choose nr as the axis of rotation. So if we do that, we have sum of torque equal to, now NL causes a clockwise or counterclockwise direction. So if we choose the counterclockwise direction as positive, then the torque produced by NL will be positive. NL is 36 centimeters from the axis of this rotation. So that's 0.36 meters times NL. And that torque is positive. The weight is 27 centimeters from the right hand. So that's 0.27 meters, okay, from the right hand. And the weight is given by mg. And mg causes a clockwise rotation with respect to the axis of rotation. This means that the torque produced by the weight is negative. So the sum of torques must be equal to 0. From here, we immediately solve NL because we know M to be 72 kilograms, so 0.36 meters times NL minus 0.27 meters times 72 kilograms times 9.8 meters per second squared equals 0. So NL is equal to 530 newtons. Now that we know NL, we can use that and plug it in there and solve for NR. By doing that, we have NR equal to 176 newtons. You can just as easily choose NL to be another axis of rotation. So if we choose NL as the axis of rotation, we have an equation for the torque as the following. So sum of torque equal to, first force is the center of gravity or the gravitational force, and that causes a counterclockwise rotation, which means that that's a positive rotation or positive torque. And this time it's 0.09 meters from the left hand. So that's 72 kilograms times 9.8 meters per second squared. Okay, and then the other torque is caused by the normal force on the right hand, and that causes a clockwise rotation. So, and that's also 0.36 meters from the left hand. So NR, and that torque is negative. And solving for NR, we get 176 newtons as well. The third problem involves a problem regarding the forearm. Approximately what magnitude force F sub m must the extensor muscle in the upper arm exert on the lower arm to hold a 7.3 kilogram shot put? Assume the lower arm has a mass of 2.8 kilograms and its center of gravity is 12 centimeters from the elbow joint. So we want to know how much force this extensor muscle is applying in order to hold that ball. To do this, we first need to identify all the forces. We already know the first force. This is the force exerted by the extensor muscle. Next is the weight of the arm. It's located 12 centimeters from the elbow joint. So here's the elbow joint. If this is 30 centimeters, 12 centimeters is somewhere here. That weight also points downward, and this is 12 centimeters. The third force is the force due to the shot put. That shot put has a weight of 7.3 kilograms, and it's located at a distance of 30 centimeters from the elbow joint. Now that we have identified all the forces, we let the counterclockwise direction be the positive direction. This is where your axis of rotation is located. So if we sum all the forces or all the torques with respect to that axis of rotation, beginning with the extensor muscle gives a counterclockwise rotation with respect to the axis of rotation. So that means that the torque produced by the extensor muscle is positive. The extensor muscle is 2.5 centimeters from the elbow joint. So we have positive 0.025 meters times F sub m. Next is the weight of the arm. The center of gravity of the arm is 12 centimeters from the elbow joint. And this arm causes a clockwise rotation, which means that the torque produced by this arm is negative. So negative times its moment arm times the weight of the arm, which is 2.8 kilograms times 9.8 meters per second squared. Finally, we have the weight of the shot put, and this weight also causes a clockwise rotation with respect to the axis of rotation. This also produces a negative torque, and this weight is 30 centimeters from the elbow joint. So we have 0.30 meters times 7.3 kilograms times 9.8 meters per second squared. And all of that is equal to 0. From here, we can easily solve for F sub m, or the force exerted by the extensor muscle. And that's equal to 990 newtons. Now, if we recall, this is a first-class lever where the force and the weight are on opposite sides of the fulcrum. You can see that the force exerted by the extensor muscle, 990 newtons, is much greater than the weight of the shot put. The weight of the shot put is equal to 7.3 kilograms times 9.8 meters per second squared, or 71.5 newtons. The muscle exerts a lot of force in order to carry a very small weight. Let's consider this fourth problem, where we have the foot. The Achilles tendon is attached to the rear of the foot, as shown in the figure. When a person elevates himself just barely off the floor on the ball of one foot, estimate Ft, or the tension on the tendon in the Achilles tendon, pulling upward, and the downward force Fb exerted by the lower leg bone on the foot. Assume the person has a mass of 72 kilograms and D, capital D, is twice as long as small d. Capital D is the distance from the ball of the foot to the downward force Fb, and small d is the distance from the downward force Fb to the upward force Ft. So we've already identified all the forces. First, the next thing we need to do is to identify where the axis of rotation is. We are already familiar with this kind of system. This is actually a second-class lever where both the force and the weight are on the same side of the fulcrum. Here, the weight is nearer to the fulcrum. So if we sum all the torques with respect to the axis of rotation, so here is the axis of rotation, what do we get? The first force, Fb, causes a counterclockwise rotation. Again, if we choose counterclockwise as positive direction, then this force, Fb, this downward force Fb, is causing a positive torque. The distance of that force is d from the axis of rotation, and the magnitude is Fb. The next force is the force exerted by the tendon on the ball of the foot, on the rear of the foot. That force causes a clockwise rotation, which means that the torque caused by that force is negative. So negative. Now the distance of that force is from the axis of rotation is capital D plus small d. And the magnitude of the force is Ft. And we equate everything or all torque to 0. Now what is Fb? The downward force Fb exerted by the lower leg bone on the foot is the weight of the person. So Fb is equal to mg. So we have d times 72 kilograms times 9.8 meters per second squared minus d plus d times Ft equals 0. We also know from the given that d is capital D is twice small d. So if we insert that, 2d times 72 kilograms times 9.8 meters per second squared minus, or let's say equal to, 2d plus d, we have 3d Ft. Okay, so d cancels out. Then Ft is easily solved to be 2/3 times 72 kilograms times 9.8 meters per second squared. Since this is the weight of the person, that's just 2/3 of the weight of the person. So that's about 470 newtons. So this force is carrying 2/3 the weight of the person, which is of course a significant amount. that's equal to about 48 kilograms. So that tendon is carrying 48 kilograms of mass, which is a large amount.